Okay, so we had begun 8.2. Which is sequences. So as I mentioned before, in 8.2, we're going to look at sequences. Then in 8.3, we're going to look at series, in particular infinite series. And 8.3 is actually quite a bit more important and has more information in it than we need than in 8.2. But in 8.2 is shorter. Obviously, nonetheless, we'll move forward. So I'm going to pick up on where we left off on page 608. So on page 608, we have some definitions of some vocabulary. And these will be words that will be sort of important to us as we're looking through the chapter and talking about things. And they are, of course, about for a sequence. So these are definitions. Let's see here. And in particular, this is terminology for sequences. So again, what is a sequence? Since we were just introducing this last session, a sequence is a list of numbers. And so we're typically going to use the notation with a big set block notation and an a sub n to represent a sequence. And so if we have a sequence, such as sequence of a sub n's, the first word we're going to look at is the idea that this sequence is increasing. So what does it mean for a sequence to be increasing? Well, it basically means that as you go down the list of numbers, they're getting bigger. So hopefully that makes sense just in a general term. We can sort of annotate this and say what this would mean. That would basically mean that, actually, let's do this. That would mean that a particular term, we'll say the nth plus 1 term of a sequence, will always be bigger than the previous term, namely the nth term. This would be true for all n, but basically it just means that every time you go down the list, the number keeps getting bigger and bigger. Then we say that this is increasing. Now, a slight different thing that we might see is if we say that a sub n is non-decreasing. So what would that mean? So again, maybe that's Abdul, if you could perhaps mute your mic so I don't have to talk over the shuffling sounds or scratching sounds, and then just put it back on if you want to join in on the conversation for some reason.
I don't know how do you?
Let's see, there should be a little choice there. Let me see if I can do it for you.
Okay.
I cannot. So if you go down to the bottom of your, oh, you found it. Great job. Thank you, sir. Okay, so in any event, if we want to say that a sequence is non-decreasing, that basically just says that there's no point in the sequence where the next number is of lower value. And so the way that looks is that if I look at a particular term, a sub n plus 1, then it could be bigger, but it also might just stay equal to the previous term. So then the restriction is that each step down the list of numbers, you never get smaller. You might stay the same, you might increase, but you don't get any smaller. Then we call that non-decreasing, because decreasing is not allowed, or is not occurring anywhere. for us to use that term. So we're just looking at each of these words and trying to see what it means about a sequence. Then we could perhaps look at some examples. And again, this box where these definitions are on page 608 just lists them all out before we go into too much detail. So let's say we just did an example of a non-decreasing term, sequence of terms. So it might be that I have like 0, and then it goes up to 3, so that's increasing, then it goes up to 5, so that's increasing, but then the next term is maybe another 5, so that did not increase, but it did not decrease either. It just stayed the same, and maybe it lingers there for a while, but then it starts to increase again, etc. So I'm just throwing down some numbers so that you can imagine that I don't want to say that this sequence is increasing because there was a period where we had 5s where it did not increase, but I can at least point out the fact that at no point did it go down in value, so that we call that non-decreasing. Okay. All right, so next up. So analogous to this is if instead of it being increasing, we could say that the sequence is decreasing. Or we could say that the sequence is non-increasing. So again, what would that mean? So analogous to the first two, decreasing means that for each term you go down the list, you always get a smaller number, a lower number than the previous one, a number that's less than the previous one. But if it sometimes doesn't do that, but instead just gives you an equivalent value, then we would say it's non-increasing. If each step you go down the list, you get a number that is less than or equal to the previous term. Never increasing, but sometimes staying the same. So then we'd say that's non-increasing. Questions about the idea of increasing, decreasing, non-decreasing, or non-increasing?
Professor, so whenever a few numbers repeat, we can either, based on if it's increasing or decreasing, we can call it non-increasing or non-decreasing.
Exactly. So when you make that sort of non-decreasing, non-increasing terminology, it allows for terms to stay the same for a while. It just prevents them from, decreasing or increasing depending on the term. Okay. So we have a couple more words on our little list of definitions here to introduce to the vocabulary. So the next up is to say that the sequence is monotonic. So monotonic means that it only moves in one direction when it moves. So basically monotonic just means that it is either non-decreasing or non-increasing. So that it only moves up if it moves, or that it only moves down if it moves. And that means that it can't be both. So monotonic means one or the other, but not both. Either non-decreasing or non-increasing. And both of those can't happen at the same time. Well, I guess they could if it just stayed a constant. Then you could have them both happen. But okay, so that's just a term. So you could say that a sequence is monotonic. And basically you're saying that it's one of those or the other, but you're not specifying whether it's non-decreasing or non-increasing. You're just saying that it's precluded from moving in one direction and only moves when it does in the other direction. And then lastly, one more. A sequence is bounded So a sequence is bounded if the absolute value of the entire sequence is limited by some number. So that the size, not worried about whether it's positive or negative or not, but the size of the terms of the sequence are restricted by some large enough number to restrict them. So if we just write up the terminology for a second to remind us what this kind of stuff looks like, bounded would mean something like, again, this backward E means there exists an M such that the absolute value of A sub n is less than or equal to M for all n. So again, I know this notation always is uncomfortable, and it's a way for us to discuss the concept in its purest mathematical form. But the primary goal here for us using this term is to understand what it means. And one of the ways to do that is to write down a mathematical definition, but usually for us, it probably means more just talking about it and understanding it. So we will refer to the idea that a sequence is bounded when we believe it doesn't head off to negative or positive infinity, that there's at some point you reach a maximum value of the sequence. Or even if it doesn't have a value that is max, there is a number that the sequence does not go beyond, either a number big enough or small enough, or positive or negative in that direction. So questions, discussions about the idea of a sequence being bounded?
I have a question.
Yes.
So if a sequence is bounded, would we be told like what M is, or is that something we'd have to figure out?
Well, you can take this concept and try to convert it into problems and how you would do them. I would save examples for that. Usually instead, we would be looking at a sequence, and we would, so again, this is the big picture for what we're trying to do throughout chapter 8 and throughout chapter 9, is that we're trying to determine whether sequences converge or diverge. Meaning, does a sequence, and I'm sorry, ultimately these will be for series, not for sequences. But that we're trying to figure out if there's a sort of a limiting value or if there's not a limiting value. And part of what will help us to do that is to determine whether the sequence is bounded or not. And it may not even be relevant what number it's bounded by. It may be more important simply that it does not go to infinity. And if it does not go to infinity, that means that it must be bound by some number. Does that help or no?
Yes, it does. Thank you.
So this is usually more easily something to think about graphically. So if I just sort of throw up a little picture up here real quick, just that you can imagine, because of your work even in pre-calculus, that you might have something like a horizontal asymptote. And before we had a function, which perhaps might be bound in some way, like let's say a function comes in and does something like this. And again, what that means is if you have a horizontal asymptote, that the function settles in on the value of that asymptote, and that often it sort of sneaks up underneath it and never goes beyond it. So it could be an example where maybe this is the line where y equals 2, and therefore 2 is an upper bound for this function that I'm showing you, in that even though I can let x go off to infinity, graphically, the function will never produce a value that rises above a 2. So then you could say it's bound above by 2. Now, of course, this is a function, so that it makes sense from our discussions in pre-calculus. But what would this look like if we were talking about a sequence? Well, then you might have values of a sequence, which we normally think of as individual points, which follow along the values of this function. So that you have a sequence of values which are settling up under a number but are bound above by that number, for example. So a numerical example could be like the sequence 1.9, 1.99, 1.999, etc. So you can imagine that this is a sequence of numbers, and that numerically you could convince yourself pretty quickly that if you followed this sequence, the limit of this sequence is 2. So this is an infinite sequence. It doesn't stop. It keeps going and going and going. But we could say that a couple of things. We could say that this is monotonically increasing and bound above by 2, just to use these new words that we've been introducing. So it's increasing because each term is bigger than the previous one. It's monotonic because monotonic just means that it only goes in one direction. And in this case, this one only goes up. And it's bound because there's a number m, namely 2, such that all the terms of the sequence are less than or equal to 2. Questions, comments, discussions about this example of using the terminology?
Yeah, Professor, you said it's monotonic and bounded by 2.
Correct. And I also said it's increasing. We could also say it's non-decreasing, which is a weaker statement. But in this case, not only is it non-decreasing, but it's even more than that, it's actually increasing because there are no values that just repeat. So monotonic is a very weak statement. It just means that it's either non-increasing or non-decreasing. In this case, the sequence of 1.9, 1.99, 1.99 is non-decreasing. So that means it is monotonic. And then a stronger statement is that it's non-decreasing to specify which of those two it is. And then a stronger statement is to say that it's not only non-decreasing, it's actually increasing, meaning that each successive term is a higher value than the previous one instead of just not being lower. And then the last term to use is to point out that the sequence is bounded. And in this case, since it's an increasing function, I would probably describe it as bounded above, meaning there's an upper limit to the values of these increasing terms, or an upper bound, I should say, of 2, that it never goes beyond 2. Questions, comments, discussion? Okay, so let's go ahead and maybe try to see what they ask of you after giving you these definitions, or look at one of their examples. So they have, whoops, let's change colors. They have an example on page 609. In which they say, consider you have a sub n equal to the sequence of 1 minus 1 over n, which is infinite, so that starts when n is a 1 and heads off toward infinity. So, as we've been learning with sequences, it's nice to have a formula for the sequence, an explicit formula, because then you can just plug in any n value you want to see what number of the sequence you have. But sometimes it's hard to understand by looking at a formula what the pattern is or where we believe the sequence is going. So one of the standard things to do to understand a sequence when given the formula for it is to try to write out the first, few terms of the sequence to see where it starts and where it seems to be going. So in this case, if we wanted to write out the first few terms here, so if I plug in n is a 1, I get 1 minus 1 over 1, which is 1 minus 1, which is 0. When I plug in n is a 2, I get 1 minus a half, which is a half. When I plug in n is a 3, I get 1 minus a third, which is 2/3. When I plug in n is a 4, I get 1 minus a fourth, which is 3/4, etc. Okay, so does anybody want to try to look at our little list of words and see which ones might apply to this, to try to use our new vocabulary and language to just discuss a sequence. Anybody willing to shout out a try there?
Increasing.
So increasing seems to be getting bigger and bigger each time, right? Definitely doesn't look like it's decreasing. And we could try to sort of look at this analytically, because what you're doing is you have a 1 here, and then you're subtracting from 1 a number, 1 over n, where as n gets bigger, the value of that fraction gets smaller and heads down towards 0. So the thing that you're subtracting is a half, a third, a fourth, a fifth, a sixth, a seventh, an eighth. You're subtracting less and less. And so since you're subtracting less and less, the remainder of what you have is getting bigger and bigger. So I definitely think it makes sense to say that this is increasing.
Could you also say that it's monotonic since it only moves in one direction?
Absolutely. So in fact, just again, to be clear, monotonic means that it's either non-increasing or non-decreasing. And note that that's a weaker statement than to say whether it's increasing or decreasing. So any sequence which is increasing, decreasing, non-increasing, non-decreasing, those are all monotonic. Okay, so we have a monotonic increasing sequence. Anything else we can say about it?
Just to clarify,
Yes, ma'am.
so when you say monotonic, you don't have to state if it's non-decreasing or non-increasing? Like, is that just a given?
The word doesn't include that information. Whether you'd have to state that or not is based on the goals of the problem.
Okay.
So the word monotonic doesn't tell you which way it's going, only that it only allows direction up or down, one or the other. It doesn't tell you whether it always goes up, so it could be increasing, or it might just be non-decreasing. It doesn't tell you whether it's going up or down. It just tells you that it's precluded from moving in one direction. That's the only thing that word means. So it's a pretty weak statement. But any sequence which oscillates, like anything with like a sign that goes back and forth, or a positive, then negative, then back to positive, none of those would be monotonic. So it does have some merit, it does have some value, but it doesn't include in it information about the direction. So, you know, if you're trying to describe a sequence, you might start with the idea that it's monotonic and then try to see if you can get something more specific in your description after that. Anything else we can say about this sequence, or are we done here?
I guess you could specify that it's non-decreasing because we put down monotonic.
Yeah, that's true. I would say that once you've said it's increasing, that sort of automatically includes that. So we could just look at each of the words and see if they apply. But if I was describing, you know, sort of the sequence, I might say monotonically increasing or something like that. Now I will want to point out though that we should see that this is also bound. Anybody want to see if they could comment on how the sequence is bound?
Take the limit.
Well, if you took the limit, what would you get?
1.
1. So the thing to recognize here is that this is heading toward a 1, but that it's always less than 1. Because you're always taking a 1 and subtracting something from it, right? So we have 1 here, and then you're subtracting a number. It just so happens that the thing that you're subtracting that makes it less than 1 is reducing in size. And that means that the values themselves, if you imagine if we extended this sequence out a little bit, you'd get like 99 over 100, 999 over 1,000, somewhere down the list, because the number on top is always one less than the number on the bottom. Another way to write this sequence is we could have written it as terms of the form n minus 1 over n, where the numerator is just one less than the denominator. This is what you would get algebraically if you just took these two terms and got a common denominator and combined like terms and combine the fractions. So what does that mean in terms of our new language? We would say this is an increasing function that is bound by 1. Is that okay? Questions at all about that? Okay, so let's do this. I'm going to introduce a theorem, which is actually 2 pages in advance, because the best time to say it is when the language is fresh in our mind before I distract you with something else. So, and then we'll come back to the pages that we skipped over. So theorem 8.5 on page 612. States that a bounded monotonic sequence converges. So what do we think that means? Do we think we could interpret this? Anybody want to try to give us a stab at saying what we think it means?
Would it mean that like any sequence that's bounded has a finite value?
That's close. So again, what do you mean when you say a sequence has a value? Since a sequence is a list of infinite numbers,
Would it be a limit?
that its limit has a value, that it has a limit that exists. So the word converges, again, for a sequence means that the limit as n tends to infinity of the sequence is equal to some number L. That's what the converges part means. And what that means is that if you go far enough down the list of the sequence, that the numbers get infinitely or arbitrarily close to some number L. So in the sequence in this that we have above here, where we did say that it was monotonic and that it was bounded, so that what one of you pointed out was that the limit of this sequence is 1. So that means it converges. It converges specifically to 1. So yeah, so the basic idea here is if you have monotonic means that the sequence, as you change the values of the sequence, as you're going down the list, they're only allowed to move in one direction. They may stay the same for a while, but when they do change value, they only increase or they only decrease when they're changing values, just depending on whether it's monotonically non-decreasing or non-increasing. So monotonic means that when there's movement or change in the value of the terms, it's only allowed to go in one direction. So just for the sake of thinking about that, let's say it's monotonic in the upward direction. It's non-decreasing. That means it may sit there at a particular value for a while, but whenever it goes up, whenever it changes, it has to go up in value, and that it's only allowed to go up in value when it does change. So that's, let's say you have that kind of monotonic non-decreasing sequence. So if you add to that that it's bounded, that there's some restriction as to how far it can go. So that would mean in this case, it's when it changes, it only increases, and there's some upper limit that it never surpasses. There's some limit as to how high the value can get. So if you put those two things together, that it's only allowed to increase when it changes in value, and there's some upper limit beyond which it does not go by. When you put those together, that means that in the end, as you go off toward infinity, it must approach a specific value. It must converge to some number. You cannot keep increasing and be bound without settling on a value. At some point, you have to pick a number and get infinitely close to that number. That's the idea. This is a very, very powerful theorem and will be used moving forward conceptually when we want to be able to draw conclusions about whether there's a limit of something. Questions, comments, discussion? So the basic way to think about this is that if something, for example, only increases as you go down the list and head off toward infinity, if that occurs, then the sequence only has two choices. If you're going to keep increasing, then your only two choices are that you increase off to infinity and you grow without bound, or that you actually settle in on a number. You can't keep increasing without either going to infinity or settling in on a number like 1.9, 1.99, 1.999, 1.999. That settles on 2. Or this limit right above here, 1/2, 2/3, 3/4, 99 over 100, 999 over 1,000. That settles in on a 1, gets infinitely close to 1. Okay, so that's theorem 8.5. And I'm going to go back. Questions about any of this so far? Comments, discussion before we look at a particular kind of sequence of note? Okay, so let me clear this page. Okay, so now we're going to focus on a particular kind of a sequence that's going to show up a lot, and it's going to be pretty important to recognize when we have this kind of a sequence. So this is introduced on the very bottom of page 609, but then quickly discussed on 610. So let's look at page 609, 610. This is the idea of a geometric sequence. Oops. Okay, so what is a geometric sequence? So it's a sequence. So we have an a sub n. It's a list of numbers. But it's a sequence in which the way you get to the next term in the sequence is by multiplying by a number. So we talked about how to describe a sequence either with a formula or by describing it recursively, where you say how to get to the next term. So if I use that type of definition, it means where the n plus 1th term, the one after the nth term, is arrived at by taking the previous term, the nth term, and multiplying it by some constant number that doesn't change. In this case, we use the r for that. So let's put an example on this. So let's say you have a sub n plus 1 is equal to a sub n times 3. And let's say that the first term is 5. So this tells us that every time I go to the next term, I multiply by 3. So that would mean that a sub 2 would be equal to a sub 1 times 3, which would be equal to 5 times 3, or 15. A sub 3 would be equal to a sub 2 times 3. So we just figured out a sub 2 is 15, so that would be 15 times 3, or 45. So once you recognize that you can think about the pattern as just saying, oh, I just multiply by 3 every time, and I started with a 5, if you see that comfortably, you could probably write out the terms without going to all the work of what I just did up here. You could just say I had a 5, and then each time to advance, I multiply by 3. So that would be 15, 45, 135, what, 405? I'll multiply 135 times 5, 405, 1215, etc. So this is an example of a geometric sequence. And again, the key property that makes a sequence a geometric sequence is the way you get to the next term is take the previous one and multiply by the same constant number every time. So we use the constant, we use the letter R to represent the constant because the R is for ratio. So take note here. Oops. That if I solved for R here by dividing both sides by a sub n, I would get that a sub n plus 1 divided by a sub n is equal to R. And what that means, if you look at it, is that if you take any term in the sequence and divide it by the previous term, you always get the same answer. Since you multiply by the same number every time to advance, that means if you went back and divided by the previous number every time, you'll get that value. So that, in this case, would mean, for example, that 45 divided by 15 is 3. 15 divided by 5 is 3. 135 divided by 45 is 3, etc. So the reason that is helpful to recognize is that if you are looking at a sequence of terms and you're trying to figure out if it is geometric, you can simply apply that test. You can take any pair of successive terms and divide the one down further on the list by its previous one and see if you always get the exact same value. If you do, then that's the number that's being multiplied each time along the way to advance the sequence, and that it is then a geometric sequence. Because they have what we refer to as a constant ratio of successive terms. That the nth plus 1 term divided by the nth term always comes out to be the same number. Okay, questions so far? All right, so the reason these are so important as a particular kind of sequence is because basically the terms of the sequence are spots on an exponential function. So for example, if I took the sequence that I just generated here and I wrote it formulaically, then I could write that a sub n started with a 5 and then multiplied a 5 by 3's. So to get the nth term, I have to say how many times did I multiply by 3 to get from the 5 to the nth term. And as we've sort of looked at before, each time you take a step in the sequence, you advance the n count by 1. And so to go from the first term to the second term, I multiplied by 3 once. Then to get to the third term, I multiplied by 3 again. Each time I multiplied by 3. And so to get to the fifth term, for example, because this is 1, 2, 3, 4, 5. To get to the fifth term, I took the 5 that I started with and I multiplied it by 3 4 times. So the number of times that you multiply by 3 to get to a particular position lags behind which position you're at by 1. So to be at the nth term, I would have multiplied by 3 n minus 1 times, which I can annotate by making that the exponent on the 3. And then what you can see if you look at this is an exponential function where you have an initial value and then you have an exponential multiplier where the variable is in the exponent. So this is an example of an exponential growth model because we're multiplying by a number bigger than 3. If the number I was multiplying by was less than 1, then the value I started with would be getting smaller every time, and then we would have exponential decay. Questions about this? Okay, so in example 3 on page 610, they just give us a few examples of these and they say just to graph them. So they're asking you to graph these because they want you to recognize that these are exponential growth or exponential decay functions. Graphs are in the book. I'll leave that for you to take a look at instead of trying to recreate them here. But let's still look at the examples. So in A, they give us the sequence where you have 0.75 raised to the power n. So if I put in a 1 here, I get 0.75. If I put in a 2, then I get that number squared, which means I multiplied by another 0.75. And as n increases 1 by 1, you keep multiplying by another 0.75. So in this sequence, you can imagine the first few terms if you like. 0.75. And then without doing the arithmetic, I'd get 0.75 squared, 0.75 cubed, etc. So that you can see that each successive term is 0.75 times the previous one. So that's why it sort of fits the recursive definition of a geometric sequence. I guess I will pretend to make a crappy little graph of this real quick so that we can also discuss some properties. So what does this look like? So if this is perhaps a 1 up here, then at the first one I'm at 0.75. And if I square 3/4, I get like 9/16, which is a little more than half. And if I add another, I get 75% of that, and 75% of that, etc. So you can possibly see that these points would sort of lie on an exponential decay function. But nonetheless, in the sequence, you are just using the points themselves in a sequence. Questions, comments, discussion about that? Okay, so let's have some vocabulary fun of our 6 terminologies for sequences: increasing, non-decreasing, decreasing, non-decreasing, monotonic, or bounded. Which ones could we apply to describe this geometric sequence?
Decreasing.
Decreasing, each term is lower than the previous. In fact, because we have a nice little multiple of a decimal, each term is 75% of the previous one, right? Which is less. So definitely decreasing. Any other words that make sense here?
Monotonic. monotonic?
Monotonic, it only moves down. It's not allowed at any point to go upward in direction. So we could put those two together and say that it is monotonically decreasing. But of course, decreasing implies monotonic, so you don't have to put them together. But just to sort of get used to the words. And anything else?
Is it also bounded?
It is bounded. So the interesting thing is if we try to apply the definition of bounded where we're supposed to come up with an M value, you might be looking at this and say, hey, it's settling down and going towards 0. So you could say, for example, that it's bound below by 0, but the definition just says we need to come up with an M that is greater than or equal to the absolute value of all the a sub n's. So could somebody provide me with a number M that's greater than or equal to all the terms of this sequence?
1?
1, yeah. So even though it's moving down, it is because the numbers never go into negative territory, the size of the numbers are always less than 1. That's kind of the way to think of what the M does, is it limits how big the numbers could get in either the positive or the negative direction. So we could say that this sequence is bound by the number 1, that it's decreasing, monotonic and decreasing. So then theorem 8.5 would tell us that it therefore must converge to a number. And that we could see in this case, both looking at it graphically, if we like here, that if I took the limit as n tends to infinity of this sequence, that I would get 0. And so that the fact that we would get something is guaranteed by theorem 8.5. In this case, we can basically see that if you keep reducing to 75% of what you had before, you're going to shrink away to nothing eventually. This is an example of exponential decay. Questions, comments, discussion?
Wait, Professor, what did you take the limit of right there?
The sequence, I put a sub n, but a sub n is defined right above it. So let me see, a sub n is this.
Okay.
And I just drew that conclusion kind of based on the graph, but you could also try to do that algebraically as a kind of a nice little refresher of your algebraic problems. We're going to have sort of a formulaic idea of the limits of geometric sequences shortly, which is going to take care of all that anyway. So, other questions at all? Discussion, comments? Okay, so yeah, geometric sequences are very, very important, but we're introducing the idea of one now, and then in 8.3, which we'll talk about later today, they come back up again and become very important for series. When you have a geometric series, meaning the sequence in the series is geometric. But in the meantime, this is all we do in this particular section. So now we have a dilemma, dear students, that I want to ask you to chime in on. So we have a couple of topics that are discussed briefly in the remainder of this section that quickly take this up a level of notch conceptually for work that we're not going to delve into too deeply. Meaning they put in a couple of things that I think most students will find pretty challenging. So we can look at some examples of how to do them. But at the same time, as I said, most of the meat of what we want to talk about today is in 8.3, not in 8.2, because they throw these at you literally on the last like 2 pages of the section or even a page and a half. And so we just have to take this with a bit of a grain of salt, okay? So Yeah, so let's see if we can do that. So the first thing I would point out in this advancement of the section is we have, oops, let's go back to black. We have theorem 8.4, and as you can note from the numeration there, that's actually before the theorem 8.5, which we talked about a minute ago, because bounded monotonic sequences converge. That right before that, they give you a squeeze theorem for sequences. Squeeze theorem for sequences. So the squeeze theorem for sequences has about the same value and import or impact on our work as the squeeze theorem did for limits back in chapter 2. Meaning that if you ever remember having seen it, by now you've probably forgotten it. Not everybody. At the beginning of our semester, I did have a couple of students refer and talk about the squeeze theorem. So it's definitely had an impact on some people's minds, but it's not something that we really use on a regular basis. We will have an opportunity to use this a little bit later in the chapter, but we will re-envision it then at that time. So they're introducing it now because they can, not because it's very important to us. So basically the way the squeeze theorem worked is that, let's say in the terms of before, when we had functions, you had like an f and a g and an h function, and that g was trapped between f and h. Then if f and h had a limiting value, then g was forced to have that same limiting value. So the same thing is said by sequences. So let's reinterpret that for sequences. If I have a sequence a sub n and a b sub n and a c sub n. So I have 3 sequences. And for the life of the terms of these sequences, meaning for all n, a sub n is less than or equal to b sub n, which is simultaneously less than or equal to c sub n. So the b values are trapped between the a and the c values. That's where the squeeze comes from. So if this is the case, and in addition to that, you have a limiting value for a and c, the limit as n tends to infinity of a sub n, and the limit as n tends to infinity of c sub n, they both have a limiting value of L. So the a values are all less than b. The c values are all bigger than b. Both of those sequences approach L, then that forces the limit as b tends to infinity of the b sequence to also be L. It has no choice but to go to L because a and c both go to L and b's just trapped between them along the journey. So this is the restatement of the squeeze theorem. So, yeah, I mean, you can sort of look at this graphically, I suppose, real quick, just to put an image in your mind. But again, my goal is to introduce or remind you or show you what the book is going to show you here, but spend as little time on it as possible. So let's say you have some b sub n, and maybe the b's, you know, are bouncing around a little bit in value. So they're sort of chaotic, and it's kind of hard to imagine what's going on with those. They seem to be getting smaller, but it's hard to say. It's hard to apply some formula to them. And then let's say, so these are the b sub n's. And then let's say you have some a sub n's. I guess the a sub n's were the smaller ones, so I'll put those down there. And you have some c sub n's. And the c sub n's are always bigger than the b's. And the a sub n's are always lower values than the b's. But in my little graphed case, if the a sub n's, as you can imagine, are approaching 0, and the c sub n's are also approaching 0, and you know that, then that means the B sub n's, which may have more chaotic behavior, but as long as it's restricted above and below by limiting values that end up going to 0, then the B sub n's have to go to 0 as well, but they have no choice but to also go to 0. Crappy little picture there. Anyway, so that's the squeeze theorem. And so if we take a quick look at how they apply this, we'd look at example 4 on page 611. So they ask us to consider a sequence B sub n given by the formula where you have cosine of n divided by n squared plus 1. So what happens here is you have a cosine function, which we normally think of as a nice continuous function, where we get this nice curve of values. But in this case, we are plugging in whole numbers, not even nice multiples of pi or anything. We're plugging in 1, 2, 3, 4, 5 into the cosine function. And so you're going to get this chaotic behavior like similar to what I've graphed above, where the sequence values are sometimes positive, sometimes negative, because the top term is producing odd numbers on the cosine function, and the cosine function goes back and forth between a 1 and a -1. But sometimes it's 0, and sometimes it's a 1, sometimes it's a -1, and in this case, it will always be something in between there, because n will never be a nice multiple of pi. It'll always just be some number on the sine curve somewhere. But you do have the situation here where this numerator is trapped between a +1 and a -1. And the denominator is, as n gets bigger and bigger, is heading off toward infinity. So you have a denominator of the fraction growing very large in size, 100, 1,000,000, 1,000,000,000, while the top is never bigger than never has an absolute value bigger than 1, and is like a little positive or negative number. So that would make the kind of graph that we see up here for our B sub n. So, but if I was trying to take the limit of this, I don't really have any previous work that we could use where we knew what to do with this cosine up here. So instead, what you would say is that, well, no matter what we have here is always greater than or equal to -1 over n squared plus 1. And it's always less than or equal +1 over n squared plus 1. And both of those we can show have a limiting value of 0. And so then by the squeeze theorem, the limit as n goes to infinity of this B sub n's has to also be equal to 0. So that's their example 4. Questions, comments, discussions about that? Okay, so now we're going to look at 2 last things that they discuss in this section and see how much we can look at them and spend as little time on them as possible because they're covered. You might have some problems in a homework assignment, but they're not really crucial for what we're doing going forward. And that is a review of the idea of growth rates, which was done with functions back in chapter 4, I think. And then okay, here we go. And the epsilon delta definition of a limit of a sequence. So growth rates is on page 614. And then literally on the very next page, the epsilon delta definition of limit, page 615. And they introduce it and they give you one example all on the same page, and that's all they do, and then they just go right to exercise problems. So both of these are literally done on one page, because on page 616 you have section exercises. So I'm just pointing that out because we're just trying to deal with the I don't know what to say, the reality that they put something very challenging on here real quickly and then move right on. So growth rates is a theorem, theorem 8.6. And epsilon delta is, as it says in what I put in the title, is a definition. So theorem 8.6 looks completely analogous or almost the same as the growth rate stuff that they did back in 4.7. So let's sort of say, I'm going to put up here like 4.7 growth rates. And so those, they talked about sort of functions and the limits of functions, for example, as you went off to infinity, which function grew faster than other functions and things like that. So they do the same thing here. So we're going to talk about a sequence. And so the idea was that we will say whether one growth rate of one thing is higher than a growth rate of another, and they have a big ordered list in this theorem. So let's look at an example without recreating the whole list. So we say A sub n has a higher growth rate or faster growth rate, or however you want to refer to it, than does B sub n if the limit as n tends to infinity of A sub n over B sub n is infinite. So again, this is a concept from before. It's hard to recall it quickly if you don't remember it at all. But the basic idea is when two sequences are going off to infinity, we want to basically pick winners. We want to basically say which one is heading to infinity at a faster rate. So this creates a list of which things grow faster than which other things. And so let's look at an example on the list, and then we'll look at specific example of functions. So, so let's say we had like powers. Consider the sequence n versus the sequence n squared. So if I'm thinking about these as a sequence, this is obviously as n goes from 1 to infinity. So the numbers in the n squared sequence are getting bigger faster than the numbers in the n sequence because they're squared. So instead of 1, 2, 3, 4, 5, I have 1, 4, 9, 16, 25. So the question is this, do these larger values increase in such a way that we would say that it has a higher growth rate? And the way we can check that is by taking a limit of a quotient. So if I note that the limit, as n tends to infinity of n squared divided by n, so I'm doing what this shows here. I'm taking the limit of the quotient of the terms. So because this becomes the limit as n tends to infinity of just n, and that therefore goes to infinity, run out of page space. So then therefore, the sequence of n squared has a faster or higher growth rate than the sequence of n. So that this would be sort of the winner with the faster rate. So there's just a list of ones to compare and examples of how to do that on page 614. Questions about that?
So I have a question. So basically you took the limit of just the denominator?
No, so what happened is that when I made the fraction, it reduced to n.
Oh, I see.
That just happened to match the denominator, but I just reduced the fraction and took the limit.
Oh.
Does that make sense?
Yes, thank you.
Now, I will point out, just as a reminder, when you make quotients where the numerator and the denominator both go to infinity, this is one of the most common situations where you use L'Hopital's rule to evaluate the limit.
So we put them into a quotient to figure out which one goes faster, basically.
So again, you're thinking about what you would need to do. And most of the time for these problems in the theorem, they give you a big list of what beats what. So that the simpler thing is to just look in the list and see which one is higher than which on the criteria that they give you in the list. So this, we can see the idea of what's going on in this example, but for most cases, you're actually just going to look in the list to see which one is bigger. And you can use this the other way around. If you see in the list that, you know, the first one in a quotient, that the first one is bigger than the second, then you know the quotient must go to infinity. Or if the bottom one is bigger in growth rate than the top one, then the fraction must go to 0. So really, you're just going to use the theorem, and they just do one example and then they immediately move on. So I'm tempted to, you know, discuss this with you and show you examples, but again, it's like literally one single face of one page with one example. So instead, I'd like to ask that you look at their example, understand from our discussion what they're talking about, but then you'll see in the example, you just look it up on the theorems list that they give you from slowest functions to fastest functions and use the theorem to do their problems. And then again, you know, if you have questions, we can talk about that later, like in my office hour tomorrow, or you can ask somebody on NetTutor in case they know about it, or we could even talk about it next week, even though by then you might have a problem on this due on your assignment. Anyway, so I'm trying to sort of, I know you guys are trying to think what kind of problems I can do, but I think their examples are pretty straightforward in that, and I don't want to do 2 or 3 more examples at this point. I'm just worried about our ability to cover the material. Especially because the very next page has something even worse for most students, which is the epsilon delta definition of a limit. So let's try to take a look at that. So how quickly can I go to the top here? Okay, so on the next page. So for those who have no memories or only nightmare memories of the epsilon delta definition stuff done in chapter 2, we have a brief little revisit of that that's literally 1 page long because the book dare not go any further. So let's consider the idea that if I want to say that the limit as n tends to infinity of the terms of a sequence a sub n is equal to some number L, I have to ask myself, what does that mean? So we have an idea behind it. The idea was basically that as n gets larger and larger and larger, the terms of the sequence a sub n get closer and closer to whatever that L value is. So what does that mean? So just to sort of write the idea, and again with the notation that's used in the limits, this means that if you give me any epsilon, no matter how small, and this is written that for all or for any epsilon greater than 0, that there exists some sort of a delta. Again, this backward E means there exists a delta. That's not a good delta. Also greater than 0, such that and again, this means for any or for all, and this means there exists so what's going to happen? Okay, I'm already messing this up. Sorry, guys. I'm doing the epsilon delta definition of a limit, but we want the actually epsilon n definition. So I apologize. Let me erase a little bit of this and modify it. Oops, I didn't mean to get this such that. So we're taking the limit as n goes to infinity. So as n goes to infinity, for every epsilon greater than 0, there exists a natural number n such that. Sorry. There we go. This is there exists. So what happens basically is that as little n gets bigger and bigger and bigger, then the a sub n value gets closer and closer to L, meaning the difference between a sub n and L shrinks away to 0. So the way we write that is that no matter how small epsilon is, for any epsilon greater than 0, and we're thinking that epsilon is a teeny little number like a 10th or a 100th or a 1000th, that the difference between a sub n and L is less than epsilon whenever your choice of n is big enough, and big enough means bigger than capital N. So lots of logic in here. And again, this is a definition. So literally, you would use the definition if you wanted to be rigorous to show when a limit for a particular sequence has a particular value. And it's very hard to understand the idea of how to apply this to problems if you don't know what the language means or what the idea of a limit is. So just some brief history, the way this is covered in the book is that they introduced the idea of a limit in chapter 2 in 2.1, 2.2. They give you an early definition of a limit to wrap your mind around it. And then after 8 sections in chapter 2, 2.1, 2, 3, 4, 5, 6, 7, 8 of working with limits and using limit laws and evaluating tons of limits. At the very end of chapter 2 and 2.9, they go over the epsilon definition of a limit. So here we are back to this place where we've been working with sequences for a bit, and we've been working with limits of sequences. We've been evaluating limits of sequences. And now they're just on this last page in 8.2 for one page only. They remind you that you can be more formal about this and use an epsilon definition of a limit. So that's, they give you an example. So let's consider example 7 on this very same page, 615. Everything is done on this one page. It's hard to believe as that is. It says, using the formal definition, consider the claim that the limit of a sequence they give you is 1, and then show that with the change. So sort of basically using the definition. Show that the limit as n tends to infinity, and the sequence they have is n over n minus 1 is equal to 1. So they're telling us the value of the limit, telling us that this limit is 1. The goal is not to calculate the value of the limit. The goal is to show that it's true based on this epsilon delta or epsilon n definition above. So the idea is we have to find a capital value n. We have to say, well, if you give me any epsilon, no matter how small, there exists, and I can find a number n that forces this to be true. And so this is the thing that we need to satisfy here. And so the way you write something this out is you basically just say, okay, let epsilon be greater than 0. We need n so that that's true. We need an n, and now we put in the specifics. We need n such that the absolute value of the sequence, which is n over n minus 1, minus L, the L value of the sequence is 1, is less than epsilon. So we get to make the little n value as big as we want, bigger than any arbitrary some number n, to make this less than epsilon. And then we have to basically figure out what that would be. So that's the setup. For those who are trying to follow along and hang in here, any questions about the setup of this? Okay. So basically the way you typically do this is you have to solve this for n in terms of epsilon. We have to figure out what restriction on n would we need to make in terms of epsilon. So we need the choice of big N as a function of epsilon, meaning you give me an epsilon and I figure out what n I would need to make this happen. And in order to come up with that, we basically try to solve this in terms of n, or say what restrictions on n would we need to have. So if I simplify the inside a little bit here, I can get a common denominator. I can make this as n minus 1 over n minus 1. So I can combine these two things in here. Since that's just a 1, that's the same as n minus 1 over n minus 1. And then I can do the subtraction because I have a common denominator here. So that would give me the absolute value. So on the top, we would have, let's see, n minus 1 minus n would be a 1, because that's n minus n plus 1. And then on the bottom, we have the common denominator of n minus 1. And we need this to be less than epsilon. So I'm simplifying what's in here to make it something that I can work with more easily. So now, assuming that we choose some n value to be greater than or equal to 2, because we're assuming we're going to go down the sequence of ways, the thing to notice is that this is always a positive quantity because n is always a positive number. So I don't have to worry about this being negative. So I just need 1 over n minus 1 to be less than epsilon. And I know both of these are positive. So this is an inequality. And so I can sort of multiply both sides by the denominator and divide both sides by e to sort of try to manipulate this a little bit. This then converts to 1 over epsilon is less than n minus 1. Again, I can multiply and divide both of these by an epsilon or n minus 1 because I know that they're both positive, so I don't have to reverse the inequality when I do that. And so that this tells me that n has got to be larger than 1 over epsilon plus 1. So I think probably most folks are lost already, but for those who are trying to follow along, any questions about how I did this or how we set up this goal?
Yeah, so where did the n is greater than or equal to 2 come from?
Well, I just want to point out that n is a natural number, and if I actually looked at the first term of n equaling 1, then the expression in the fraction would be undefined. I'd have 1 over 1 minus 1, which is 0. So I'm putting in that restriction because you can choose, in the end, what are you going to do? You're going to pick an n value, a capital N value here, right? And you're going to say that what I need to have happen is that whenever little n is bigger than capital N, this is true. And I'm assuming n would be like 1,000,000 or 1,000,000,000. So I'm only going to be considering little n values that are very large. So I can certainly make the notated restriction that I'm going to only accept a capital N value that would force little n to be bigger than or equal to 2, just so that this thing is always non-zero and positive. I know there's a lot of logic in here. I kind of feel I would be drowning you guys with this problem immediately. I want to somehow address it because I don't want to ignore it and pretend it's not there, because it's there. Some students will take it on, some students will not. It's, again, one page only. But that's where we are. That's why we are where we're at. And we're going to need to move on probably within the next 5 or 10 minutes to try to sum this up and just suck it up and move on. Such is life. But nonetheless, we got a couple of minutes here. Other questions about how I got to this point? So basically the idea is I want to choose an n value, a capital N value that forces this to be true. So based on this fact, I let, whoops. So I let capital N just be any natural number bigger than 1 plus 1 over epsilon. So if I choose n, and again, you give me an epsilon, like let's say, you know, epsilon was 1/10. Well, then 1 over 1/10 is 10, and 10 plus 1 is 11. Then I would choose capital N to be 11 or 12 or anything bigger than 11, basically. 12, 20, 100, and it would work. So this gives me a way to choose my capital N value to guarantee that once I'm past that point in the sequence, the difference between the sequence values and the limiting value L will be small enough. In this case, the limiting value is 1. So then note, this is sort of the justification. For any epsilon greater than 0, if capital N is bigger than 1 plus 1 over epsilon, then when n is greater than capital N, then n will be greater than 1 plus 1 over epsilon. And then you just follow the work that we did up here backwards. So I'm starting now with the fact that this is true, and I follow this line of logic back up that way. So that means that n minus 1 will be greater than 1 over epsilon, which means that epsilon will be bigger than 1 over 1 minus n, n minus 1, sorry. Oh, I've switched these. Hang on. Yeah. So then epsilon is greater than 1 over n minus 1. Or 1 over n minus 1 is less than epsilon. I can reverse the inequality by just changing the sides. And then that, from the work I did above, converts to the fact then that 1 minus 1 over n minus 1 is less than epsilon. And that's what we were supposed to show. That was the conclusion that we wanted to reach up here. So we needed to show that there's an n such that n over n minus 1, I need to go one more step. Which means that the original n over n minus 1 is less than epsilon. And then we typically write what's called QED, which basically means that we're finished with the justification or the proof or whatever you want to call it. QED stands for Quo Erat Demonstrata, which is Latin, which basically says I demonstrated the thing that I was supposed to demonstrate. So yeah, I don't know what else to say. That's the problem. Much as horrific as it looks, that's they do this example.